While stars are often depicted as luminous balls of gas, this is not the end of the stellar story. Today, we turn the page to investigate what remains after stars die. Simplified life cycle of a star. We have already covered the life cycle of stars in a previous video, but let's summarize everything. Most stars fall into a general category known as the main sequence. Their masses depend on the mass of the original gas cloud that ignited to form the star. Small stars, known as red dwarfs, slowly fizzle out into white dwarfs over an obscenely long time. Medium-sized stars like our Sun expand rapidly, shedding their outer layers in a planetary nebula, while the core remains as a white dwarf. Giant stars end in a spectacular supernova explosion, leaving behind a neutron star or a black hole. Note that we will not go into black holes in this video, as there is a future video reserved for the topic. White dwarfs. White dwarfs are the stellar corpses that 97% of all stars will end their lives as. They are arguably the third most extreme objects in the universe, after neutron stars and black holes. The surface of a white dwarf is composed of carbon and oxygen, or possibly even oxygen and neon. Although they cannot generate nuclear fusion as their parent stars could, white dwarfs retain most of the thermal energy released by the reaction, heating the star to at least 100,000 Kelvin. Because white dwarfs can only transfer heat through radiation, the most inefficient type of heat transfer, white dwarfs remain insanely hot for billions to quadrillions of years. White dwarfs have masses that range from around 0.2 to 1.4 solar masses, yet it is compressed into an object the size of the Earth. A white dwarf is so dense that a single teaspoon of white dwarf matter has a mass of 5.5 tons, or the mass of an elephant. The extreme density of a white dwarf causes it to have extreme gravity, which can be up to 350,000 times that of the Earth at the surface. This causes the atmosphere to sink to the surface, with the molecules comprising the atmosphere being segregated based on their masses. While regular stars are sustained through the balance between radiation pressure generated by nuclear fusion and gravity, white dwarfs cannot generate radiation pressure. Gravity crushes the white dwarf to such an extent that the electrons comprising the atoms are squeezed together. A fundamental principle of electrons is that no two electrons can occupy the same space if they share the same quantum properties. This is known as the Pauli exclusion principle. Therefore, the closest electrons can get to each other is when they are barely grazing each other's surfaces. In a white dwarf, the electron degeneracy pressure, the manifestation of the exclusion principle upon electrons, is what stabilizes the star. As long as the star is not too massive, gravity cannot overcome the electron degeneracy pressure, and the star exists as degenerate matter. If more mass is added to a white dwarf, it shrinks in volume to accommodate a greater effect of gravity. There are several ways in which a white dwarf will end. Over billions to trillions of years, white dwarfs are projected to slowly cool down until they become black dwarfs. Black dwarfs are spheres of electron degenerate matter that does not emit any light at all. It is important to note that black dwarfs are merely theoretical objects, as the lifespan of a white dwarf is longer than the current age of the universe. There are endings that are far less gentle though. White dwarfs are often found in a binary system, where an often younger star orbits the white dwarf. If the white dwarf draws enough gas from its companion, it can ignite nuclear fusion at its surface, generating an explosion known as a nova. Novae are common, occurring around 10 times a year in our galaxy. The white dwarf is not destroyed in the explosion. However, there is a cosmic mass limit for a white dwarf. The maximum possible mass for a white dwarf is around 1.44 solar masses, known as the Chandrasekhar limit. If a white dwarf manages to steal enough gas to surpass the Chandrasekhar limit, the electron degeneracy pressure is no longer able to overcome the force of gravity. The added gas briefly ignites the fusion of carbon in the star before the white dwarf explosively collapses in a Type 1a supernova explosion. Neutron stars. If a star's mass lies between 10 and 25 solar masses, it will collapse in a Type 2 core collapse supernova explosion. We have described the process in more detail in our Stars Explained video. What remains of the stellar core is a neutron star. Unlike white dwarfs, which were sustained through the electron degeneracy pressure, a neutron star is too massive to be sustained in this way. Instead, a neutron star is sustained through the neutron degeneracy pressure. Neutron stars are the densest things that are not black holes. Their great mass is compressed into an object 20 kilometers across, or the size of a city. That's equivalent to Mount Everest compressed into the space the size of a sugar cube. The intense density of a neutron star causes it to possess an extremely strong gravitational field, around 100 billion times stronger than that of Earth at its surface. The intense gravity causes passing light to be bent around it in a process known as gravitational lensing, allowing scientists to peer at both the front and the back of a neutron star. The structure of a neutron star greatly resembles that of planets, with a 10-centimeter thick carbon atmosphere draped over a solid crust, with a core at the center of the structure. The crust is composed of iron nuclei left over from the supernova, mostly composed of neutrons, hence its name. The crust is incredibly strong, estimated to be around 1,010 times stronger than the strongest materials on Earth. Scientists have observed that small irregularities on the crust, known as mountains, fractions in millimeters in height due to the extreme gravity, many times more massive than the Himalayas. These mountains generate intense gravitational waves, ripples through space-time, as a neutron star spins. Neutron star mountains may be the cause of starquakes and breakages in the neutron star's crust, as the mountains interact with the unimaginably powerful magnetic fields. As we dig deeper into the crust, the nucleons rearrange to form long cylinders and sheets, known as nuclear pasta. Rather than individual nuclei, neutron stars are composed of gargantuan compilations of nucleons that resemble gnocchi, spaghetti, and lasagna. Beneath the nuclear pasta is the core of the neutron star. Currently, scientists are not completely sure what the core's structure is like, as it is impossible to peer into them. However, the core is most likely to be composed of a quark-gluon plasma, a state of matter where the nucleons dissolve into their elementary particles. We have described more of the concept of states of matter in a previous video. Quarks, the fundamental particles that compose protons and neutrons, come in 6 different types. We will discuss more of elementary particles and their interactions in a future video, but all you need to know right now is that 2 types of quarks, the up and down quarks, compose stable matter at normal conditions. In the cores of neutron stars, though, the pressure is so extreme that some quarks may morph into strange quarks, forming a state of matter known as strange matter. Strange matter may be contagious, and it is incredibly stable. If enough strange quarks turn about, it may begin to convert more particles into strange quarks. Neutron stars contain the most powerful magnetic fields in the universe, which are trillions of times more energetic than the Earth's. Within a certain distance of the neutron star, atoms will be compressed into pencil-like rods, guaranteeing the death to anyone who approaches the neutron star. A subclass of neutron stars are magnetars, which contain magnetic fields that are over 1,000 times more powerful than a regular neutron star. Pulsars are a common subclass of neutron stars that have twin beams ejecting jets of radiation. As the poles of the twin beams may not be aligned to the poles of the neutron stars may appear to flash as the radio beams pass. Over billions of years, pulsars will radiate their energy out through gravitational waves and slow down. Like the Chandrasekhar limit for white dwarfs, there is a critical mass for neutron stars, after which the neutron degeneracy pressure cannot prop up the star against gravity. This limit, known as the Tolman-Oppenheimer-Volkoff limit, or the TOV limit for short, is around 2.2 solar masses. If the neutron star's mass surpasses the TOV limit, it collapses into a black hole. Many neutron stars exist in stellar binaries, where they orbit another star. Often the companion star is lighter and younger than the neutron star, and the neutron star steals gas. Once the mass surpasses the TOV limit, the neutron star cataclysmically explodes into a black hole. A small number of stellar binaries exist as neutron star binaries. Over millions of years, the 2 neutron stars' orbits decay until they hit each other in a kilonova explosion and form a black hole. Twinkle, twinkle. While the twinkling lights floating high up above seem eternal, one day they will all die. In the end, stars are reminders that everything will come to an end.